Suppose a plane flies at 100 kilometers per hour. Is that enough information to predict where it will be in 1 hour? No. A plane flying east and a plane flying north can have exactly the same speed but end up in completely different places. The number does tell us how much magnitude or distance is covered in a certain time, but in physics, direction often matters just as much as magnitude, if not more sometimes. So that begs the question, how do we describe quantities that have both? So we will learn this today in our 30-second lecture, Why Vectors Exist. Just a heads up, this lecture is different as I had a friend of mine make it for me as I'm overwhelmed with exams and studying. So it will be different than usual, but the instructions and script were mine and he followed it, or so he said, and from what I've seen, looks fine. So, quantities that are fully described by just a value or a number are called scalars, like this word here. So, like 5 kilograms, 20 degrees Celsius, 10 seconds, nothing else must be specified because the number and the unit contain all the information, or to turn it around, we can't really add a direction to them. Sure, temperature or energy can be negative, but that's orientation, and we will get to that. So, scalars are the numbers that only have magnitude or length. So, we waited 10 seconds. We know what that means. We couldn't say, oh, you waited north or east. You know, that type of question. Now, some quantities require more information, like velocity, like force, like acceleration, electric field. For those, we use vectors. A vector combines magnitude and direction and orientation. But sometimes we say that direction already consists of orientation too. So we kind of like just say magnitude plus direction most of the time, okay? So its length, it's its magnitude, and the way, the angle, basically the position, the slope itself is the direction, including the orientation. So this is different than this. But basically, we usually draw vectors as an arrow or arrows, and the length tells us how much of something it is there. So a vector with magnitude 15 is longer than the vector with magnitude 3. And then orientation tells us which way it's facing. So let's see this horrible sketch to understand it. This arrow is a vector x. This marking x, which is invisible. So this marking x with a half arrow on top is how you mark a vector. Its magnitude is the length, well, usually x. So now for numbers that's different. For instance, its length could be 12 or something, but yeah. It's slightly more complicated than this, but we will get to that in this lecture. Its direction is the line on which it is located. So like an infinitely long line going from up and down, marked with gray dashed line, or blue on this display for some reason. It basically tells us on what axis it is lying. X-axis, Y-axis, Y equals 3x axis, etc. Or on a globe, north-south axis, east-west axis, etc. So in our case, this arrow is on up-down direction, or sorry, axis. As for, this determines the direction. As for orientation, it tells us in which of these two components of the direction the vector is facing. So if the direction is up-down, that's a horrible way to write up-down, but yes, then orientation will say whether it's up or down facing arrow. Of course, in future references, I will be referring to vectors as quantities with magnitude and direction. The latter will be a combination of direction and orientation. So, for instance, vector pointing down will be how I referred to the direction. So I tell you where it's pointing, and then up and down, you just figure it out yourselves. Because, well, that makes sense that it's the same direction, but different orientation. So now that we've covered magnitude and direction, this is where most people kind of get vectors wrong. A vector is not a point or just a point, because this becomes relevant later on. If we have a vector's magnitude, so its length, and then direction, of course with this I mean direction and orientation, they are identical. They are the same vector, regardless of where they are in space. So our three vectors here, they do not start in the same point, nor do they end in the same one, but mathematically they are equivalent and define the exact same vector, because their length is identical, because I just copy and pasted them, And then I just move them around, and their direction is basically the same as is their orientation. They're all pointing towards the right, and they're all on the horizontal x-axis. So if we draw a horizontal line, they're all gonna be on it if we just move them around. For instance, I can move this vector here, and it's still the same vector, regardless if I move it or if it's in the same position. So imagine taking a short walk. First you move 3 meters to the east and then 4 meters to the north. Your final position is different from where you started, but yeah, here's where vectors would come in. Your motion is, if done as I said, separated into two directions, east-west and north-south. They do not interfere, as in if you move along one, you are not moving along the other. In this situation, even the ancient Pythagoras knew that the diagonal is the shortest path in such a triangle-like movement. For instance, like this. Oh yeah, I draw it here. So regardless of what we choose as our starting position, for instance, that be our home, or the store, or maybe even the car dealership, whatever you want, if you take the same path, the overall distance is gonna be the same. That's kinda, you show that. But now that that's covered, how would we describe these numbers, since we cannot calculate with arrows and images? We have a few challenges, of course. We need to have a way to preserve the magnitude, aka the distance, and the direction, as in north, south, east, west. So like left, up, right, side, down, whatever. So we need to remember these instructions and somehow word their math with it. Because, sure, we can say move 3 meters east, but how will you calculate that? Let's look at our walk again. We will replace meters with units for simplicity's sake, and we say we moved 3 units along the horizontal component, aka east-west direction, and then 4 units along vertical or north-south component, and we will get something like this. Of course, for the sake of it, imagine the arrows at the end of the lines because, well, I do not know how to make them in Desmos already. I do have a website here on the bottom of the website display, and it's also going to be in the description of the video, and it's great for learning vectors, but I did not have the time to master it well enough to use it. But yeah, I recommend this site. This site, I absolutely recommend it. It looks amazing. Perfect. Well, you have to play around with it a bit. So here are our arrows. And if we did add the diagonal here, we see that this, or any diagonal, can be described by two directions, two arrows that are at 90 degrees angles. And with combinations of their magnitudes or lengths, we can define both the magnitude of the green arrow along with its direction, since we remember the trigonometric functions and slope, etc. Moving in the horizontal direction for 3 steps is a vector in itself, and then moving in vertical direction for 4 units is a vector in itself, but the overall movement can be described by one vector comprised of both of these values, aka the coordinates are defining the vector. So with that, if we set the origin point from where the vector goes, so starting position, at 0, 0, then the coordinates at which the arrow ends are the vector. So our green vector will mathematically be written and calculated with as 3, 4 on screen in orange. Of course, whatever we move this green vector, like wherever we move it, up, down, left, right, the endpoint will always be 3 horizontal and 4 vertical units away from the origin, like this. This green vector, the new one, is the same as the one before, just moved up and right, because we see that the difference between the x coordinates is 3, and the difference between y coordinates is 4. Now, let's reinforce this a little bit, because what is the difference between the point and the vector now? Well, the point tells us where we are, while the vector tells us how far and in which direction we should move. Points are marked with capital letter followed by their coordinates, while the vectors are marked with marking, the arrow roof one, that equals to the coordinates. So it's important to not confuse the two. For ease of understandings, I'll use I'll just use these two markings in my lectures. Sometimes I'll just write the vector as this, and then in the top of the slide I'm gonna add one vector, so it's easier to like understand that everything in the slide is referring to vectors instead of points. And I'll specifically try to focus on points being marked like this, okay? There's also some markings like these, so normal brackets would represent the points, and these arrow pointy brackets would represent the vectors. etc. So keep that in mind and be careful because that's online. Certain sources use these for vectors. As for me, I'll use the previous marking as I've shown for vectors and points. And of course, I'll explain what I mean. Now, working with vectors. So let's see what happens when we work with 2 points, or the path to them being vectors. Let's say we walk along the vectors 3, 4, so 3 horizontal units, and 4 vertical. And after that, we will walk for another vector of 2, 1. So obviously we ask ourselves, what was the total distance from our start to this current point? Not the distance we traveled, but the distance between the start and the ending. So if we went in a straight line, we can find out this very answer by graphically placing vectors one after the other. So placing the beginning of the second right at the end of the first. And we get this. Our path ends on 5, 5. So I drew the first vector. It's at 3, 4. And then the second one, 2, 1. This is one of the ways to graphically add up 2 vectors. We technically already did it when we found out the green vector at the start. And it also works with non-right triangles. That green vector was kind of like an introduction to why those coordinates are useful, because they help us preserve both the direction and the magnitude at the same time. I should have said that earlier. My bad. Anyway, that was how you add up vectors graphically. It's called a triangle method or tip-to-tail method. I prefer the triangle method because you kind of make a triangle one. The second one is parallelogram method, where you put both vectors in the same origin, like the top image shows. And then you draw parallels to the other one. So like you draw a copy of U at the end of V and then a copy of V at the end of U. And where they end, touch tips, you draw from the origin to the tip, the arrow, and that is the sum of the 2 vectors. It's basically an overcomplicated triangle method, so we will be using the second one. So this one, the triangle method for addition. Because it's also better for multiple vectors, because you can easily just place vector 1, vector 2, vector 3, and then connect the start of the first one with the ending of the last one, and that's our result vector. Okay? Super simple to remember. So now let's see the numerical addition. So we know that the result must be 0.55, because, well, here I showed it. These same vectors are gonna have to add up to 5, 5. Because we just shown it graphically. Let's make sure to know why this happens math-wise. So the numbers did. And if we analyze it for a little bit, we see that 3 plus 2 equals to 5, and 4 plus 1 equals to 5. So it's not that hard. We see that the second vector gets added to the vector 3, 4, and then the sum is 5, 5. So we will end up individual components separately, and we will get our result. Why is that? Well, for that we need to know unit vectors. Remember when I replaced meters with units at the start of the lecture? Well, in vectors, these units are called unit vectors. The following image is from the thumbnail of the organic chemistry tutor, which explains this topic super well. So I do recommend it, but basically, in x direction, the unit is unit vector I, like here. In y direction, it's j, and in z direction, it's k, or it's the other way around. You have to draw this and then just make sure to be consistent with it. Depends on how you use it. I think I use I for x, j for y, and k for z. This graph kind of misleads it a little bit, but yeah. So when we write out the vector v, as it's shown in the image, we would multiply those individual units per axis with the component. So we see that we have Vx, which is the x component. So in this case, that's 5, 3, or 2. Ignore this 4 here. And then we would multiply that to the I vector. So we would get this one written as 5i. And then we would add the y component. So again, 5 with unit vector j, kind of like this. The components are scalars, so just numbers, they're magnitudes, and they do not have direction by themselves. And when we multiply them to unit vectors, we get vectors that, when added together, give us the vector v itself. This is just an oversimplified summary. The video does it way better, so again, check it out. We will use this in physics sometimes. I will mention them later and near the end, but not as good as he does, so just keep in mind this video is amazing. So now for subtraction. Subtracting a vector means adding its opposite. The opposite vector has the same magnitude but points in the opposite direction. So something like this, and then we want to subtract this vector. We would just multiply this vector by -1 to get, we would get this vector, and then we would just add these two vectors together. And if we move this one here, the subtracting result would be something like this. So while the addition would be something like, if I place that one there, that would be like this, I think. So this is addition and this is subtraction, kind of. Move this one here or move the inverse of this one. Anyway, the opposite vector has the same magnitude but points in the opposite direction. Subtraction often appears when comparing positions or velocities. So basically you're adding the opposite of the vector. So kind of like this. We have subtraction between a and b. So we will turn the b into a negative b, and then we're gonna draw vector a, and at the end of vector a, we're gonna carry over the green vector b and get the subtracted result. If we wanted to do this, the sum of them, well, we would just do something like this. So we see that the sum is this and the difference is this, kind of like this. You see the graphical showcase. Next up is scalar multiplication, or multiplication with a number or a scalar. What is it? Well, let's say we have a vector v, and we multiply that with 2. What would that do? Well, we can assume it would double its length, and we would be correct. But how does this affect our new coordinates? It doubles them. So a product of some number to a vector gives us each individual, that's a c times vectoral component x, and then vectoral component y, like this. Our original vector has coordinates 3, 4, meaning our by Pythagorean theorem, which is how we will determine the length, its magnitude is 5, because, well, 9 plus 16 is 25, square root of 25 is 5. If we double it all, the new length should be 10. And if we do 6 squared plus 8 squared, we get 100, which is indeed 10 squared. This begs the question, can you add scalars to vectors? Well, let me answer this back with another question. Can you add mass to time? No. Well, you can, but they're not gonna add up together because the units are not compatible, so you do not achieve anything. But with multiplication, scalar multiplied to a vector gives a vector, so kinda like that. We will also see why that is in a bit. I think I definitely covered that and explained it with unit vectors. Same with negative signs, so that way you can flip the direction of the vector by multiplying by -1. Because let's say this is 1, 1 vector. If this is the origin 0, 0, and then we just draw this, if we multiply this by -1, so both of these become -1, -1, the arrow is here and the coordinate system is moved here. And this becomes 0, 0, and this becomes -1, -1. So let's showcase an easy physics example. We're not gonna be solving it yet because this comes with physics, but we will see why vectors are useful. So we see that the box is being dragged under a 30-degree angle. That's one vector applied to the box. The second one is the gravitational force pointing downwards. Now, the box is on the ground, so it cannot fall further down. There is something called a normal force that is pushing back, opposing the gravitational force, because, well, as we're going to learn, wherever you're accelerating, that's when the forces are present. If the box is sitting still, acceleration is 0, so technically the sum of the forces should be 0. And of course, lastly, we have friction, which is opposing the pulling force. And in such a system, we define which forces, or in our case, vectors, have the same direction, so up, down, and left, right. We see that pulling up, down are normal, gravitational, and y component of the pulling force. Because we're pulling at an angle, we're pulling the box upward slightly, so that contributes, making this normal force lesser than the gravitational force. Okay? So that's the force that the ground is acting on the box. Yes, something like that. And then left and right, we have the x component of the pulling force and friction. And then again, the difference between the two is acceleration, but We'll get to that. Basically, we separate into two axes to determine what is the vector in each respective axis, so then we can easily add them up, because if we want to draw all these 4 vectors in one line, we would get 1, 2, 3, 4. And of course this sum is like this, which is very easy, but if we just sum up, down, we get multiple equations, which makes it easier to solve systems with multiple variables. I'm overcomplicating this. Basically, we would add those vectors together to see which way the sun is pointing, and that's where the box would be moving. Now, for last part of this lecture, extracting information out of a vector. So first things first, how long is the vector? How do we determine it? How do we write it? We already know that. Oh yeah, this is the marking. The markings in this slide are referring to vectors. Anyway, we will be solving the magnitude or its length with Pythagorean theorem. How would we mark it though? What even is vector's distance? Is the distance from origin to the given point. But we know how to mark distance from the origin or 0, don't we? Absolute value. So absolute value of vector represents its magnitude, and the direction is a scalar, a number representing the length. But logically, it makes sense. Absolute values will always give out a positive, just like a distance makes sense to be positive. Because we remember absolute value of x means that we're looking for a number that is x units away from 0. So this is x units away, and this is x units away. X and x, the directional one. Of course, this is minus x and this is plus x, so these two vectors have the same magnitude, so their length should also be the same. It checks out, right? So using the idea, our x squared plus y squared is length squared. Then the square root of both sides, mark that distance with absolute values, and we get the formula. And for example, the vector 3, 4, 3 squared plus 4 squared is 9 plus 16, which is 25, and the square root of that is 5. So, yes, the distance, we know that, now to explain what is said on this slide, we know that Pythagorean theorem states that a distance of hypotenuse is equal to, well, the square of that is equal to the sum of the squares of the other two sides. Oh shit, this is a nice triangle. Crazy. So if we replace the markings, so replace the v with absolute value to refer to the distance of the vector itself, because we have to translate into vector space, and insert this into this formula, which is just this one edited, we get this. And this is our formula for the magnitude or length of a vector. Now, to say more on unit vectors, let's say blue vector, or in this case, white vector, is our unit vector. It is defined with length. No, that's green. Am I colorblind? So these small vectors are unit vectors. They are defined with length 1, so their magnitude is 1. Our white vector v is slightly more than 4 unit vectors long, so its magnitude would be something like 4.05, I guess. Basically, we can write any vector as an extended or shortened unit vector, or a sum or difference of two that aren't parallel. What do I mean by that? To get the unit vector, we would divide a given vector, like that one before, with its magnitude or the length. And as silly as that sounds, this is called normalization. It is the process of scaling a vector so its length or magnitude becomes exactly 1 while preserving its original direction. A normalized vector is commonly known as a unit vector, as I mentioned several times already, and it's highly useful in like gaming, physics, even AI to isolate pure directional data. So like in AI, how far is some concept in which direction? So you get axis of like cat and dog axis, and then less cat is, I don't know, human, and then less dog is a guinea pig or something like that. That's horrible. Basically, so 2 legs, 4 legs, and then wings and no wings. Basically, like that system. And it's like, oh yeah, butterflies have wings, and what's that, like 7 legs? So multiple legs and wings. Butterflies are here. And then no wings and 4 legs, that's cats. And that's also dogs and horses. And then we have pigeons, and then we have humans, and then we have etc, etc. So this direction where the vector is pointing to, that is important, and then that is preserved with unit vectors. Basically, they're used to tell us the direction of a new vector. For instance, in gravitational force between two objects, the formula has an extra factor of vector of the distance between the two bodies divided by the distance itself. Number-wise, that factor is 1, because the distances just cancel out, and the units do too. It's just there to tell the vector's direction if we decide to draw it or compute using vectors. For instance, the force itself is multiplied to, what did I say? Distance between two objects, vector distance, and the distance itself. So this marking is kind of the same as this marking, so you're not getting confused too much. Basically, this is how you get force. Basically this. Yeah, we're gonna get to that in physics more as well. But yeah, so if we imagined a breakdown of a vector into unit vectors, it would look something like this. Multiplying the number of the value on x-axis with the unit vector of the x-axis, I, and then the number or value on the y-axis with this vector on the y-axis, j. So let's say this is the x-axis, and this is the y-axis, and then we have I, and then we have 2I, and then we have 3I, that's a horrible 3, and then we have j, and then 2j, etc. And then the vector would be like, oh yeah, this is 3I plus 2j, and this is our vector. In this case, it's 3I plus 4j. Oh, I'm lagging out a bit. But yeah, so it's another way to write vectors, which makes addition even easier to explain. So actually, let's solve an example, adding vector u to 1 to this one. So we have our vector v and our vector u. We rewrite them with unit vectors as a sum of unit vector parts, and then we're gonna add these two together. And then this is the v vector and this is the u vector. So now we will color code those that have the same unit vectors, and we're gonna add those two separately together, and we're gonna get this. The result would be written as, do I have it? I do not. The resulting vector would be 5, 5. That's it. Now, you could use this method to also explain why multiplication works, but we're gonna get to that because there's a special type of multiplication. But first, how are two vectors aligned? How do we determine that? Well, we know that two lines can be parallel, perpendicular, or any other angle. So to answer this, we need a new operation. This is a dot or scalar product of two vectors. The result is a scalar made out of the product of the magnitudes of two vectors and the cosine of the angle between them. Why? Well, oh yeah, in geometry, like parallelograms or whatever they're called, or even triangles, when you want to make a projection of a certain side onto another, like we see on the image here, we are drawing a perpendicular line to the side onto which we are projecting a desired side. And then this line meets the end of the side. Here we go 90 degrees up from vector v towards the end of vector u. And then the distance from the start of vector u to this point here is called projection of, wait, I lost myself. Yeah, the distance from start of u to intersection of the vertical line and v, that distance is called projection of u onto the vector v. I think I write it out later. I think I do, yes. So what does that scalar result tell us? Well, magnitudes are positive, as they are a result of absolute value. So cosine of the angle determines the sign of the result. If the result is positive, then the vectors are facing to the same side. So like the image here, or the angle between them is less than 90 degrees, we know that the vector is going to be pointing in the same side, sort of. So like this, we know that both vectors are facing like this, and the angle is less than 90 degrees. If the product is 0, so this result equals to 0, then the angle is exactly 90 degrees, meaning it's perpendicular, And it makes sense because if we want to project this line straight down, the distance between this point and the projection this point is 0. Kind of makes sense. So 90-degree angle, 0 product, the result of multiplication being 0, they're perpendicular, and if the results are negative, then the angle is greater than 90 degrees, and vectors are pointing away. This formula is more useful when you factor out the cosine of theta to get the formula for the angle between the vectors, such as this. Of course, there is another way to multiply them, and that is by their components. Like we said before, you can just write them out as vector components, so we have xa times I plus ya times j times, and this is like a bracket, x b I, and then plus y b j, and then you multiply all these together, you get x a x b I squared, which is a vector multiplied to itself, which basically gives us 1. And then we have plus, I think that's like this one times this one and this one times this one, and we have the cross product of two vectors that are 90 degrees apart. So the angle between these, the angle between I vector and j vector is 90 degrees. Per this formula, if you multiply them together with a dot product, you get 0. So the term xa times yb and yaxb are 0, meaning they're ignored. So it's basically like complex numbers multiplication. The middle part gets cancelled out. So the first part is, so the result of this multiplication will basically just be the parts where the vectors, the unit vectors, are squared, because that's the only result we would get a value out of, kind of. Yeah, basically. So, but yeah, you can just also use the c times vector rule. So you multiply this to each one, and then you just essentially multiply the x component of each vector together and then y component of each vector together. Oh yeah, actually, for your homework, do the multiplication. So do this multiplication between vectors v and u from before. I forgot what they were. I think there were 3, 4, and 2, 1. Yeah, do this multiplication for these two with unit vectors, and then for product of unit vectors, use this rule to determine what the actual result will be, okay? But basically, I can also rewrite, so this is the up part, and I can rewrite the distances, or the magnitudes, as Pythagorean theorem ones, so I get the individual value for the magnitude of vector A and magnitude of vector B, and multiply it together. If I set a fraction of these two values, I will get the cosine of theta, or the angle. So just knowing the coordinates of the endpoints of vectors, or to be more precise, those coordinates we set define them as if the vector starts at 0, 0, and its end coordinates will be higher by their respective x's and y values. But yeah, if you just know those coordinates, you know you can solve for their angle between them, basically. Yeah, that's about it for this formula. This is good to keep in mind. It's very useful to remember. I think this one is easier to remember though, so either of those, you can just turn them around. That's it. So, as I said, if they're facing the same direction, the result will be positive. If they're perpendicular, the 90 degrees one, the result will be 0. And if they're pointing opposite, it's gonna be negative. But what about parallel? What's the determinant, the step that determines if they are parallel or not? Either same or opposite direction, so parallel and anti-parallel. They are parallel, either of those two, if there is some scalar c that is a real number, such that the following is true. So if we can extend, shorten, or flip by c being negative, a vector to get the other one, so basically if the ratio between their y's and x values is equivalent, and of course z if we have 3D vectors, then they are parallel. So if we can find a certain constant that we would multiply to one vector to get the other one, or multiply to the other one to get the first one, then that. Basically, this formula is useful for determining if they're parallel or not. Yeah, basically. So now back to projections, because I didn't explain them before. Since it seems that my friend thought it would explain them now and not before, because I had to edit the slides slightly to make them readable for me. Basically, what is a projection? First, imagine it's like a light shining straight down. If we imagine an obstacle in its way, like a vector, then the shadow of that obstacle is its projection onto A, so the ground. And as we see here, I marked a subscript that small white a is the line onto which we're projecting. So this vector is marked with projection onto A of vector V. Kind of like this, if you want to remember it. And that's it. There was only one slide dedicated to this. So now on to the hardest and best part about vectors, cross product. Before this, we multiplied vectors like scalars. Sort of. Now let's add geometrical application to it. For scalar type of multiplication, we use the dot. However, for this type, we use a cross, an X. This is why this is called a cross product. Now, what would that even mean? First of all, we have to establish some rules. If we multiply two lengths together, we get a surface of a shape that's defined by them. So for a square, if we multiply the length of side A to the other side, we get the surface. But what happens if we do this here? Do we get the surface of the square or any other shape that they might form if we multiply them? Technically yes, but also no. The result of this product is a vector, because it's a vector multiplication. More on that yes part from before in a bit. So here it's very important which one is written first, because unlike the dot product, addition and so on, this multiplication results get different if we change the order. So vector v times vector u is not equal to vector u times vector v. So just keep that in mind. Why? For solving it, we use the right-hand rule. So have your index pointing finger pointing in the direction of the first vector of the multiplication. So in our case, v, or here a. And then the middle finger is curved inward, pointing to in the direction of the second vector, b. And then after you set this up, your thumb, if you extend your palm like on the image, is gonna be pointing upwards. Or, well, whichever direction it is, that's where the product is facing. On the image, that's C. On our example, that's W. If you switch the order around, so we start with A, and then B is on the other direction. So for instance, if we started with B, it would basically turn this way 90 degrees. So our index finger would be this direction, that would be A, and then B would be pointing, this should be B for this second example. I'm writing it in lower capitals for some reason. Yeah, basically. This is B, and then A would have to be pointing that direction. And for that, our thumb would have to be pointing downwards because, well, you're inverting it, kind of. So that would be this product. So yeah, the first vector is the index finger, so the pointing one, and then the middle finger is the second one, and then the result is the thumb. This also works for any angle that's like between 0 and like 270 or even, 180 if your flexibility allows it. But it works for any angle, even 25 degrees. As long as like your hand orientation is right, the vector is correct. But yes, the product is a vector pointing where the thumb is facing, so perpendicular to both vectors. I think that means, yeah, it's 90 degrees to both of them, yes. This explains that if we switch the order around, our thumb would end up pointing down, meaning the direction of our W vector, or C on the image, would have the opposite orientation. And this is how you determine its direction. So for this type of product determines the direction mainly. As for its magnitude, well, here the surface comes in play. The magnitude of the product is equal to the surface of these two vectors. Like the surface that they draw if multiplied. So vector A and vector B, if we multiply them together, we would get some surface. This surface, the value that the surface has, is equal to the magnitude of the vector that is perpendicular to it, if that makes sense. This is called a normal, like we said before with the force, because it's pointing out of the center. I'm not gonna confuse you with that. Basically, since these two vectors aren't always perpendicular to each other, we will be using sine of the angle to compensate, and we'll get our formula that the magnitude of the product, so the result of this product here, is equal to the magnitude of each individual vector times the sine of the angle between them. So if you ever have a writing of the cross product of vectors a, b, that equals to the magnitude of a times magnitude of b times sine of the angle between them. Basically. You can also derive this formula if you want, why this is the way it is. Don't bother. It's one of those that's easier to just remember the way it is. So now for the finish line, it's a small teaser for next time, as next time we will learn what matrices are and why they're useful. But a short intro to them is that a matrix is a rectangular arrangement of numbers, symbols, or expressions arranged in rows and columns. It acts as a compact, organized way to store data, represent complex systems of equations, for instance, or perform geometric transformations such as on vectors. Basically, it's an organized spreadsheet. Anyway, here is the mini test. Just a couple of basics, basic math basically, yeah. So this lecture was enough for us to build foundation for the vectors in physics. I could mention orthonormal basis, but that would be overcomplicating the topic, which we already need like basics of. So you can read up on it on your own. So orthonormal basis, very useful, but we don't need that right now. But yeah, thank you anyway for tuning in to today's lecture. I hope you have a great rest of the weekend, yes, and I'll see you all on our next quest. Bye!